Hello student, welcome to the class. Let me show you how to access the web page of this class. First, please start your browser. I usually use Google Chrome because I use a lot of Google services. Let's start Google Chrome. In the Google Chrome, you can type my name, Hyoung-Goo. Yes, Hyoung-Goo. This is my name. And then search my name. Then the first result. You can click the first result. This is my web page. Next, you can go second link, teaching. Click teaching. Then you can see the list of the classes. Now, please find year 2007 for Introductory Mathematics for Economists. Now, this is our web page. This is our class web page. The link to this page is this one. So you can simply copy and paste this one to the browser. You can reach exactly the same website, our class website. Next, the second one, class folder is at this link. So let me click this one. Yes, you can see the list of class materials. Let me change this one into list view. So the order of this class materials or structure of this class material is exactly in line with our class schedule and syllabus. This is our first class. So let's click class 01, introduction. Now you can see our class presentation slide. You can watch this presentation file with Google browser or other web browser. More conveniently, you can download this file. You can go to File and Download, and then download to PDF. Let me download this one into the PDF. It is downloading. So let me open the folder, and then let me start this one. Open with PDF viewer. Yes, this is our class material, the first class material. Yes, it is a full view. Again, the class web page is at this link, and our class folder is at this link. Students can find class materials and other information at the link above. Alternatively, students can reach class information by Googling my name, Hyoung-Goo. This is PDF file, and here, of course, I can log in. And then in order to log in, I will type my email address. Yes, hyunggang@ehan양.ac.kr. This is my email address. And let me type my password. This is same one, but now I can edit my slide like this, Googling my name. Alternatively, students can reach class information by Googling my name, Hyoung-Goo. Let me quote this way. Quote and unquote. Okay, again, this is our PDF file. And then students should install and learn R. Next page. I recommend this class requires students install and learn R. In order to learn R, students can watch video from number 1 to number 4 in the following link to become familiar with R. So let me click this link. So you can copy this one and then paste it. Then you can see some video content here. Let me change it into the list view. You can check 1, 2, 3, 4. Number 1, number 2, number 3, number 4. Yeah. So you can watch video number 1 to number 4 in the following link to become familiar with R. Now presentation, I also provide you with presentation slide. For the presentation slides about video number 1 to video number 4, you can click this link. Let's click. Now, learning R with machine learning. Basically, I explain how to use R with machine learning. About R, you can go to, again, Google search bar and simply type R. And then you can see this one, the Comprehensive R Archive Network, or R, the Project for Statistic Computing. You can click whatever you want. Let me click this one. And then, yeah, getting started. We want to download this one. So download, go to CRAN. There are a lot of links, so let me click the very first one. Now, download R for Windows. If you are a Mac user, of course, you can download R for Mac OS X. If you click this one, then you can find install R for the first time, and then you can install it. Once you install R, then you can see the icon like this one, and then you can click this one to start R. Right? So this is R terminal. So let me show you a very simple program. A equal 1 and B equal 2. Now A plus B equal 3. So in this class, we will use R. So let me go out. Q, you can type Q, this one, and enter, or alternatively, you can click this X. So I prefer this way, so type Q, and then no, I don't want to save the image of workspace, no. So let me go back to our class slide, first class slide. Let me close this one, this tab. I can close this tab too. And third. Now student can study, first topic is exponential function. So student can study exponential function and continuous compounding at those links. So let me go to the very first one. E, mathematical constant. This is the first topic for this class. E, mathematical constant. E is also called Euler's constant. Now the number E is a mathematical constant. That is the base of the natural logarithm. We will learn what is natural logarithm shortly. The unique number whose natural logarithm is equal to 1. Now the E, this number, is approximately equal to 2.71828 and forever. And is the limit of 1 plus 1 over n to the power of n. So we have a definition of E. So let me show you again. So E. So E, mathematical constant E, the definition of this one, E is equal to 1 plus 1 over n to the power of n. But this n should go to infinity. Therefore, I will move this one slightly. And then I can put, let me use the red one. Now lim here n becomes infinity. Okay, this is the definition of E, and the value of this E is about this one. Very long sequence. Now, the E can also be calculated as the sum of the infinite series this way. So E is alternative definition of E is a summation from n equals 0 to the infinity and 1 over n factorial. So it is 1 plus 1 plus 1 over 1, 2 plus 1 over 1, 2, 3 plus 1 over 1, 2, 3, 4 and forever. Now this constant, the E, can be characterized in many different ways. For example, E can be defined as a unique positive number A such that the graph of a function AX has a unit slope at x equals 0. Now the function fx is called exponential function. E to the power of x is called exponential function. And the natural logarithm or logarithm to base E is the inverse function of the natural exponential function. I'll explain this one in more detail shortly. Okay, this one. There's another, in finance, we have interesting application. Okay, compound interest, continuous compounding. So, if you are interested in, you can read this article here. And in calculus, we have this one. Another interesting property of this one, of E, is like this one. About this one, let me go out and click characterization of exponential function. First, let me type exponential function. Okay, so exponential function. So exponential function is like this way. Okay, especially we are exponential function like this way. Especially we are interested in the case when B is equal to E. So let me characterize that exponential function. Okay, so Ex is basically lim n infinity 1 over x and to the power of n. So basically, so E to the power of x is lim n to the infinity 1 plus 1 over n, but here instead of 1, let me delete this one. Now important part is that now it is the x. Okay, so let me compare these two, and then actually it is very easy to derive this second characterization of exponential function from the first one. We can derive this one very easily. Let me show you. First, let me move this one. So let me delete this one for the time being. So let's calculate E to the power of x. Then it is lim and infinity and 1 to the 1 power of n, and then this entire thing you can make it to the power of x. Then it is, of course, let me write down only this part, 1 plus 1 over n to the power of nx. Now let's change this nx part. This nx equals some sort of t. Then n is simply t over x. So therefore 1 plus n nx is simply 1 plus 1 over t over x, and then t, which is the same to 1 plus x over t and t. So when n is go to infinity, then this implies t goes to infinity as well, right? Therefore, what we can write is that this is basically same to, now let me delete this one. Therefore, what we can write is that, that's the blue one, this is lim n to the infinity, and the 1 plus x, now n, and then n, right? We have this way. So we derived e to the power of x exponential function from the definition of e, mathematical constant. This is same, so ex is also can be value of, this is the value of infinite series. Ex equals n from 0 to n, x to the power of n over n factorial. Okay. Another interesting property is this one. We can define ex to be the unique number y such that this one, right? This is exactly x, ex. So what it means is that, this 1 over x, let me show the graph. You can show the graph. This is the 1 over x, and then we integrate from 1 to e to the power of t, maybe let me change the notation actually. Let me change this one to the x, and then let me change it, the name of this x-axis is t, and then it is 1 over t. So let me delete this one. So here the formula for this graph is 1 over t, and if we integrate this area, and the size of this area is exactly x, so we have this interesting pattern 1 to the ex, and we integrate this one dt, and this becomes x. So this is it. We can define ex to be the unique number y that satisfies this one. And then others are interesting one. Another interesting property of the exponential function is such that, yes, we have interesting characterization and proof. Okay. Another interesting property of exponential function is that if you take derivative dx, if you take derivative or simply ex prime, then it is ex. So very interesting property of this exponential function is that if we take derivative of exponential function, it becomes exactly the same one. So you can prove this one. You can prove this one with the definition of either this one. Yeah, you can prove either that one with either using this definition or this definition. You can take derivative of this one, this part, and you can easily see that this one is exactly same as before. Alternatively, you can take derivative of this one, then it is still the same to itself. Therefore, if you take derivative of exponential function, it becomes itself. This is a very important property. Very important property. Now, next, let me introduce natural logarithm. So let me skip to our presentation PDF version. This is more convenient. Now let me introduce natural logarithm. About natural logarithm, you can again click this one. The natural logarithm of a number is its logarithm to the base of the mathematical constant e. Okay, for mathematical constant e, please check the previous page. Now the natural logarithm of x is generally written as ln x or simply log ex, or sometimes if the base e is implicit, you can simply log x. Now the parentheses are sometimes added for clarity, giving ln x or log ex or log x. Now for the natural logarithm function, if considered as real valued function of real variable, is the inverse function of the exponential function leading to the identity. So this is important. This natural logarithm is inverse function of exponential. Actually, log is inverse function of the exponential function. So yeah, it is very straightforward. Yeah. So important one is natural logarithm ln and ex is simply x ln e, but here e is implicit here, so cancels out, so it is x. Right? So they are inverse function of each other. Inverse function of each other. So natural logarithm is inverse function of exponential function. Exponential function. But only when x is greater than 0, right? Because it's a log function. Formally, the natural logarithm a, ln a, may be defined as the area under the hyperbola 1 over x. This is the integral ln a. So integral from 1 to a, 1 over x dx. So this a is this one. So log ln a is this one. So again, this definition is consistent with our previous characterization, such that, yeah, this is the solution for ex. So it is natural. Now this function is logarithm. So we have a nice figure over here as well. ln a illustrated as the area under the curve. Area under the curve. 1 over x, so this area, from 1 to a, so basically size of this area. The size of this area is ln log a, log a. So if you, instead of a, you put ex, e to the power of x, then this simply size, the size is simply x, right? And this is same to our previous discussion. Now this function is a logarithm because it satisfies the fundamental property of the logarithm. What is the fundamental property of a logarithm? Well, in log, we can transform multiplication into the summation. Actually, that is the power of the logarithm function. ln ab multiplication is ln a, ln b. Okay? This can be demonstrated by splitting the integral that defined ln ab into two parts and then making the variable substitution x equal ta in the second part as follows. So let me see. So ln log ab is, using the definition above, it is integral from 1 to ab, 1 over x dx. Now we can split this into two parts, from a and from 1 to a and from a to ab. So integrate 1 to a, 1 over x dx plus a, ab, 1 over x dx. Now we can leave the first part as it is. Then about second part, we can change a, b, x equal ta, this x equal at, then it is at, right? So we can change with this change of variable. So we, instead of x, we can plug this over here. Now it is 1 over at and dat. But now we integrate x from a to ab. Instead of integrating a to ab, because x is now ta, we can integrate this at from 1 to b, right? 1 to b, then it's exactly the same as above. Well, exactly the same above. At, because at is from 1 to b, then it becomes ab. When it's 1, it is a. it is b, it is ab, right? So you change your variable. Now this first part is again same. About second part, we can regard this at as simply t. We can regard at and at as simply another variable t. So this one. Now this is integration over 1 to a plus integration 1 to b. So it is ln a plus ln b. So we just proved the fundamental property of a logarithm. In elementary term, this is simply scaling by 1 over a in the horizontal direction and by a in the vertical direction. Area does not change under this transformation, but the region between a and ab is reconfigured because the function a over ax is equal to the function 1 over x. The resulting area is precisely ln b. Okay, this is intuition. Now next page. Now the derivative of natural logarithm is this one. We can prove this one. By first part, fundamental theorem of calculus. The fundamental theorem of calculus is basically inverse of integration is derivative and inverse of derivative integration. So d ln x over dx, let's take derivative, then we can use the definition of ln x, then we can have this one, d integral 1 to x, 1 over t dt. But now, because of fundamental theorem of calculus, if we take derivative of this one with respect to x, is simply 1 over x, right? 1 over x. So, therefore, this is exactly inverse of integration is derivative, right? So we have the same one, so it is 1 over x. So we just proved it. Okay. For other property of the natural logarithm, log 1 is of course 0 because integration from 1 to 1. Log e is 1. It is by the definition of the identity, right? It is by the definition of the log function. And because we know exponential and log function are inverse function of each other, so it is straightforward, and we just proved this one. And then when x is less than y, log x is also less than y, log y. So log function is basically increasing function, and we have this one, and other properties are also interesting, and you can take a look at, and we can move to the next page. Now let us mind the differentiation rule. What is the differentiation rule? Okay, about differentiation rule, let's go to about differentiation rule. Let's go to this link. Differentiation rule, and then we have a bunch of formula for differentiation, right? Differentiation linear. Observe this. So I think most of the formula is very familiar to you. So hx is afx bgx. So if we take derivative, then it becomes linear function. It means that a h prime x is a f prime and bg prime. In Leibniz notation, daf dg bg is a df dx plus b dg dx. Now constant factor rule, a f prime is a f prime. The sum rule, this one, all special case of this one, linearity. Now product rule, suppose hx is equal to f and g, then h prime is fx prime, fg prime, which is f prime g and fg prime. We have this one. Now chain rule, very important one, chain rule. So h is the fgx, then h prime is fg prime, which is f prime and g prime. In Leibniz notation, we have this one. Actually, if we use this chain rule, we can prove, if we use this one, then we can prove this one as well, more conveniently. Let me show you. So in chain rule, f, g, x prime is, we know, f prime and then g prime, right? So we can actually use it. So because natural logarithm and exponential function are inverse function of each other, so we know log ln e to the power of x is the same to x, right? We know this one. So let's take derivative. Let's take derivative of each side. ln e x prime is x prime should be 1, right? So this 1, we know that. So let me investigate this part further and we can use a chain rule. So this is the, we can regard ln x equal to fx and ex equals gx. So we know f g prime is f prime and g prime, which is now log x prime, and then gx prime. But gx prime here, g prime is ex. We just discussed that one important property of the exponential function is that if we take derivative of the exponential function, it becomes itself. So it is e x, exactly the same one. It's the same one, right? Ex, and then this is equal to 1. This is equal to 1. Actually, to make it more comfortable, let's write down ex. Basically, let me write down this one again. So let's write down y equal ex, and f y is log, or here let me use ln y. So here, so f gx is of course fy, right? So let's use this one. So again, this one is the f g x equals ln e x, and then if we take derivative, we have ln, because e is y, so we have a derivative over here and ex, right? And then because of g prime is same to this one, so yes, this one, so this is should be equal to 1, and then this ex is y, so move this one, so ln y prime is y equal 1, so ln y prime is 1 over y. So we just proved. So it is another proof. So we can use the chain rule, then you can again show that derivative of log function is 1 over x. Now to make you get familiar with the exponential function, I want to introduce you, okay? Another interesting one is the Euler identity, okay? So Euler's identity actually, Euler's identity. So let me copy and paste to this our class web page. Euler identity. In our Euler identity is like this one. ei pi plus 1 equals 0. This is very interesting one. And actually, this Euler identity is a special case of Euler formula. So let's copy and paste this Euler's formula over our class web page. Euler's formula. Okay. So if we use Euler's formula, then Euler's identity is straightforward. right? Because if we believe Euler's formula, e to the power of ix equals cosine x plus I sine x, and instead of x, if we put pi, in particular when x is pi, pi is 1/2 turn, 108 degree around the circle, then ei pi equals cosine pi plus I sine pi. Since cosine pi is -1 and sine pi is 0, therefore it follows that ei pi equals -1 plus 0i, and ei pi plus 1 equals 0. So let me write down again. Very important to know Euler's. Very important to know Euler's formula. Euler's formula is that eix is cosine x plus I sine x. This is called Euler's formula. Then how to prove Euler's formula? Well, there is it. There is a proof for the Euler's formula. Yeah. Proof of the Euler's formula. Proof. Well, there are two ways we can use either power series. We will learn what it means by power series. But here, because we didn't learn power series, let me skip this part. And then we can use calculus. Using calculus, we can prove Euler's formula. This is important. So let me capture this one. Capture this one, and let's put this on our class web page. Now, proof of Euler's formula, and this one, and let me copy and paste this over here as well. So Euler's formula, okay? So another proof is based on the fact that all complex numbers can be expressed in polar coordinate, which means that suppose we have the complex number, like a plus bi, right? We can write down this one as, this is I, so this is y-axis imaginary part, so this is real part. So you can write down this one as point A, B, right? So this is A, this is B, right? Complex number. So we can transform into polar coordinate, which means that, right? We can regard this one as R. The length of this one R. R is of course root A square plus B square. Then we can put this one as a theta. Then A equal R cosine theta, and this B is R sine theta. So basically, I just show that any number, any complex number, is the point in this coordinate of real part and imaginary part, which is in turn transformed into the polar coordinate this way. So because EIX is a complex number. EIX is complex number. This is complex number. This is complex number. So which means that there must be a way to write down this one into this formula this way. So this is so therefore A plus BI is R cosine theta plus I sine theta. Okay, so EIX, because it is imaginary, it is complex number, so there must be way to write down this one as cosine theta plus I sine theta. So there is some R and some theta that satisfy this one. It should be. No assumptions are being made about R and theta. They will be determined in the course of the proof. Okay. Now, From any of the definition of exponential function, it can be shown that derivative of EIX of derivative is the IEIX, right? It is again chain rule. You can regard IXY, you can regard IX equal to Y, and then basically you are using chain rule, so Y. So basically you are Y prime is of course EY and Y prime, right? Using chain rule, but Y prime, because Y is IX, so Y prime is I, so it is IEIX, right? Because IX is Y. Okay, so this is it. So anyway, it means that it can be shown that the derivative of EIX is IEX. Therefore, by taking differentiation of both sides of this one, then the left-hand side is IEIX and right-hand side is cosine theta plus I sine theta dr dx, and derivative of cosine theta derivative is minus sine theta, and then derivative of sine theta prime is the cosine theta. You may not know this one, but let's accept this one as a formula. Then we have this one. Okay. Again, it is the chain rule, so this one. Now substituting r cosine theta, I set this one. So here, instead of this part, we can plug this one. We can plug this part. Sorry. Basically, you can plug this side into the right hand side, left hand side, and then we can compare left hand side and right hand side. We can compare left hand side to right hand side. Then it gives. Then we can figure out that this one, this part should be 0. dr over dx should be 0, and d theta over dx should be 1. Thus, r is a constant and theta is x plus c for some constant c. The initial value r0 is 1 and theta 0 is 0, right? Because r0 is 1, right? And then theta 0 is 0 comes from 0i is 1, right? Because we put we can put x is 0, we put x is 0, then, well, we have this one, right? This one, and then giving r equals 1 and theta equals x, so this proves the formula by comparing both sides. So basically we are done. Okay, this is the end of our first course. Thank you.